Okay, I think it's time to get started. Welcome, everybody. I'm Peter Weiss. I'm the Public Information Manager of AGU. And we welcome you to the AGU 2010 AGU Fall Meeting press conferences. We're starting our first one. This year we're doing web streaming. We've done that in the past, but we're doing it in a different way. We're including some video, hence the bright lights, which are blinding me and everyone else on the stage. We'll work on that. And we're also a change from the past for anybody who happens to be listening in on the web. We're not having call-in to ask questions. Instead, we're having a chat capability on the web that you should be seeing on your screen. And you can ask your questions by chat, and someone here on AGU staff will read the questions to the scientists who you want to answer. Speaking of questions, I ask that please hold all questions until all the speakers have spoken. Then we'll open up questions from the floor and also from the chat. And also, we welcome colleagues of the scientists or anyone else who's not a journalist to be in here listening, and but not to be asking questions. That's reserved for the reporters who are here covering this event. And I'll moderate the questions. So let's get started now with our first press conference. We're calling it Eruptions from the Far Side, New Global Views of the Sun. And our speakers, I'm not sure in what order they're going to be speaking in, but I'll just give their names from the press conference schedule. We have Carol Shriver, research scientist at Lockheed Martin in Palo Alto, California. Alan Title, he's SDO, AIA principal investigator and a professor of physics at Stanford University and the senior fellow at Lockheed Martin Advanced Technology Center in Palo Alto. We have Madhulika Guhatharkurta, sorry. She's SDO program scientist at NASA headquarters in Washington. And we did have Tom Bogdan on the press conference schedule, but there's been a change. Instead, we have Rodney Burek. He's the chief at the Space Weather Services Branch, NOAA Space Weather Prediction Center in Boulder, Colorado. So who's going to speak first? Okay. So Dr. You can say, Lika will speak first.
Thank you, Peter. Good morning. It's a great pleasure to be here. We are here to discuss one of the first results from Solar Dynamics Observatory first mission of NASA's Living with a Star program. Speaking of living with a star, you might know that the Earth actually orbits inside the atmosphere of the sun. In that sense, we are truly living with this star. Even though the sun appears kind of flat, motionless to naked eyes, it's only a limitation of the human eyes. Recent missions, telescopes, spacecraft have really penetrated the blinding glare of the sun, and what we are finding is unpredictable turmoil on the surface. And you're going to see examples of some of that from our most recent observations from Solar Dynamics Observatory, as well as Solar TErrestrial Research Observatory, which is also dubbed as stereo, contains 2 spacecraft. And I'm going to start showing you what do I mean by the fact that we live in the outer atmosphere of our star. Well, what I want to impress upon you is that the sun also produces, other than the light that sustains life, also produces solar wind. It spews a hot million miles per hour wind of charged particles, electrons, protons, throughout the what happened here? If it goes off, it's okay. What you're seeing are these particles emanating from the sun and there is a big coronal mass ejection that takes place, and the little dot that you just saw was Comet Encke. Comet Encke's tail gets ripped off by this dynamic solar wind, essentially. And so anything in the solar system, planets, comets, asteroids, are really in the gust of the solar wind, which can be sometimes really stormy when we have coronal mass ejections. So point number one, yes, the sun is a variable and dynamic magnetic variable star that drives every cubic inch of space to the very edge of the solar system, creating a dynamic space weather. And what I'm going to show next is, again, if it will show for a while, this is the impact on our planet when you have this dynamic pressure impinging on Earth's magnetosphere. You see it shimmer. It's like a cocoon, the magnetosphere, which protects our planet from the harmful radiation of the sun. And this is a theoretical model that shows how this magnetosphere is actually shaped by this dynamic solar wind. And when we have, again, a coronal mass ejection or a flare, everything gets really crunched in. So the next image that I want to show is, why do we actually study the sun? Well, clearly, the sun is an astrophysical object. We study it to understand basic plasma processes in the universe. You can see the top half that just shows that we are interested in what goes on in our magnetosphere, where geostorms are produced, what happens in the ionosphere, mesosphere, what happens on other planets, what happened to Mars, what happens on Venus, what produces essentially the same kind of aurorae on Jupiter or Saturn. And so the top half shows just the basic physics questions that we want to understand. The lower half shows the impacts. What are the impacts of this dynamic space weather on our present-day life? Human society has become really technologically dependent, and just about any technological advancement that we can think of, whether it's GPS, navigation system, cell phone, you look at anything, telecommunication, they are all vulnerable to this space weather effect. We have human space flight, astronauts teetering at the border between magnetosphere and outer magnetosphere, where the harmful effects of solar radiation can affect them. And even terrestrial climate is affected by particles and, of course, solar radiation. So I think we don't have a choice. Understanding solar variability to the point of predictability is crucial to our modern way of life. It is really necessary. It's not a choice for a spacefaring nation like ours. And so missions like SDO and STEREO are taking us closer to achieving this goal. And I think Dr. Title will start by showing you some of the recent discoveries we are making with SDO and STEREO together. Thank you, Alan.
Thank you, Lika. I'm going to be very brief. For about 75 years, people have discussed sympathetic flares. These are multiple flares that go off near simultaneously or near simultaneously, but don't have any apparent physical connection. People have all been seeing coronal mass ejections, and I'm showing you a few of these things that have happened in the past few days. The first event happened yesterday morning. They're very big. You can see that they cover 70 or 80 degrees, 170 degrees about of the sun. They're sort of pretty. This is about 500,000 miles, this big loop, and that event took about 30 minutes. But we didn't understand the connectivity. And people argued for decades whether flares cause these coronal mass ejections. But there were people who studied coronal mass ejections and never saw flares and said that can't be right. And this has gone around and around. And so what I'm going to do is turn you over to Carl, who'll give you an explanation. But I'd like to point out that while we observe these events on SDO, the stereo spacecraft A and B were also observing, which added a lot of richness to this event, which allow us to make this connection that Lika was alluding to the heliosphere. And shortly after this meeting, Carl and I will travel to England, where we put together a team to follow the events from the sun to the heliosphere to the Earth's magnetosphere. And I'll turn you over to Carl.
Okay, good morning. It was here briefly.
That's yours.
Okay,
It's me,
it's yours.
yes.
Is it the same presentation?
It's the same presentation, unless you've changed it.
I haven't changed anything. All
You
right.
just can say next slide, and I'll do that for you.
All right. Well, on the next slide, let me take you from the beginning, basically from the solar surface out to the Earth, and try in the process of doing that, explain what it is that we found and what the significance of it is. The solar magnetic field basically is spread out over most of the solar surface in lots and lots of little concentrations, which we can see in a variety of wavelengths. And it's concentrated in some locations more than in others. Where most of the magnetic field is, we call those active regions. And within the active regions are even stronger field concentrations that we call sunspots. And on the next slide, you can see that we have an option not just to image in visible light or in ultraviolet or extreme ultraviolet light. We can also look in polarized light. And we use polarized light to measure the magnetic field as it sits at the surface. And we can basically measure the two polarities coming out from the sun or going into the sun. And as we go higher in the atmosphere, or in this case viewing as on the next slide, what we can do with a computer model, we can see how the magnetic field lines, the lines of force, connect this one polarity to another. And as the surface field changes, two things happen in the outer atmosphere. One is the magnetic field deposits energy into the outer atmosphere, which heats it up from a mere 5,000 degrees up to several million degrees. And the next slide will show you that the advantage of that is that the corona begins to glow at the extreme ultraviolet wavelengths that the AIA instrument on SDO can see. And the second thing, and that's the key point of this particular event today, is that sometimes the magnetic field actually goes unstable and leads to huge eruptions that are associated with either flares or coronal mass ejections. On the next slide. As Alan already said, we've for years known that many of these events happen simultaneously or nearly simultaneously, and the term sympathetic flares or sympathetic mass ejections has been around for 75 years. But always based on statistical arguments. There are too many of them to be chance. And what we're going to show you over the next few slides is how we think these things are actually connected and leading to connections. So if you hit return, this particular sequence, I'll show you two examples of these sympathetic flares. This particular one is a series of three that starts in the central circle. And then if you can look at three locations at the same time, if you now hit return, it'll start playing that movie. You'll see that there are events going off at the limb in the lower right and at the upper left. So these events happen in step over a full diameter apart of the sun. So these are 1.5 million kilometers at least of solar surfaces involved in these processes. The next slide, and that's the case that I'm going to be dwelling on most of the time, begins to show you the series of events on August 1st. If you can step through one at a time, this series of events on August 1st starts with a small flare and coronal mass ejection at the X. Then the next thing that happens is that within that oval, there's a big active region that's going to go a flare, a pretty large, not extremely large, but a large flare. And at the same time, at the top of that oval, there's a filament that begins to erupt into the space from the sun into the space that the planets go through. And at the very lower end, there's another little brightening at the limb that happens at the same time in a region that isn't even on the disk. We just see the top looming around the sun. And then there's a second set of eruptions in this particular oval that starts with a filament on the right-hand side, and then an eruption way off the limb that's actually a coronal mass ejection that's moving backwards away from the Earth that can be seen by the stereo spacecraft. So if you hit it again, it should start playing, or one more time probably. You can see that series of events. There's a flare and an eruption, and then another eruption and a flare. And they happen in pairs. And if you look at this long enough, you can see even more brightenings that are happening at the same time. And Alan and I sat through this, looked at it over and over again, and started to compare things with our models. Because what we can do in the computer is interesting. I need to show you one more thing. We can actually look at these things, if you hit return again, not only from the side that we're at here at Earth, looking at the sun, but there are two spacecraft. They're labeled A and B, the stereo spacecraft, that look at the sun from the left and the right. And if you hit return one more time, you can actually see the bottom is what these spacecraft see near the sun, and the top, they in fact look at from the sun in different direction. It's a bit of an odd thing to show it this way because you're looking at the same structures, but from the left and from the right. But you can see these events go all the way through the inner planets, hit Mercury, hit Venus, and eventually hit the Earth, where they triggered a geomagnetic storm. Not a huge one, but a very well observed one. So let me take you back to what the models can tell us. We have magnetic field information, unfortunately, only from the front of the sun. And this is a magnetic map of the front of the sun, and within that circle is what we can take from the helioseismic and magnetic imager on SDO. And what we saw was that when the sun is rotating approximately once a month, that when a region that is now not quite on the solar disk rotated off the disk, there wasn't much activity going on. But a week later, when that region came back onto the disk, we saw new magnetic fields. So if you hit return again, we can do a computer experiment. We can say, well, we can look at this like we can look at it with stereo. So from stereo behind, SDO's perspective from near Earth, and from stereo ahead on the right, it's falling off because I didn't want to make these images too small. But what we'll see is we use information in that dotted oval on the right-hand side that's basically going from past to future. We knew there was nothing. We know there's going to be something later once it rotates up to the front. So we did an experiment. What would happen to the coronal magnetic field if we changed from that one state to the next state? So if you hit return, you'll see basically the set of field lines that I was showing you earlier. And what you're seeing changing isn't necessarily what's really happening on the sun, but somehow the sun has to get from the past to the future. And I'm going back and forth, so you see this over and over again. And there are a few locations where most of the changes happen. Those are locations where strong electrical currents are induced, and they're basically at magnetic fault zones, where the field has to choose. Do I go left or do I go right? Those are the points where most of those electrical currents run. Now, I'm going to take you one more step into the next thing. We can now compare these particular model field lines. Can you hit return? With the observations that we have from these three different perspectives, stereo behind, SDO, and stereo ahead, and that shows really poorly. So I'll pass by that one. But you can see this big eruption, and you can see it from three different perspectives. So the next one shows you the movie, again with these field lines, where the field is changing most rapidly. And if you now try to remember where most of these changes sit, they sit basically almost on that central meridian from the North Pole going down, where you see these fields just sweep back and forth. Those connect the first flare, the first filament eruption, the second filament eruption, and each of those field lines in fact connects to the other flare and the other major event. So if we now map this to the next and final one, I come back to this set of coronal observations that we've seen with SDO. There's one flare going off. There's another flare in the bigger active region, but now in association with, and unfortunately the lights are so bright you probably can't see this very well. So what have we now discovered? Well, for years, solar physicists, including ourselves, have been looking for the cause of these explosions basically in the region that's exploding, and that's a good thing to do. And we found a number of patterns in the magnetic field that really have to be there before an explosion can happen. You have to put energy into the environment before you can tap it and explode. It's like thinking of an avalanche. If there isn't any snow on the slope, there's not going to be an avalanche. But these observations that I've been showing you here, the ones that Alan showed, and many other examples that we have seen since with SDO, now show you another aspect. If we wish to know why a flare goes off and exactly how it evolves from the moment it begins to explode and goes into the space around the planets, you need to know not just the properties of the region exploding, but you need to look at a very large fraction of the solar surface. In fact, in this particular case, you have to look at a part of the solar surface we can't even see from Earth, but that we were fortunate to see with one of the stereo spacecraft. So maybe the reason why we're having such difficulty creating high fidelity forecasts for solar storms and the resulting space weather is in part that we're not seeing everything. We have to expand our view and look well beyond the region exploding. And for the consequences of that, I'll switch over to Rodney. I'll take this one.
I have no fancy movies or anything like that, any of the visuals. But I would like to press upon you how important this data are for a different organization. I come from NOAA. We are part of the National Weather Service, one of the Centers for Environmental Prediction. I'm from the Space Weather Prediction Center, where we do research. We have development, transitioning research into operations, but most importantly, we have our Space Weather Forecast Office. This is a 24-hour-a-day, 7-day-a-week operation. We predict space weather for a number of customers. And what I've shown here in this picture is a photograph of our forecast center from just a few days ago. You can see a few Christmas ornaments in there. But also on the left, stereo data, right there displayed, and on the right, SDO data. These data are used in our forecast office every day for developing the forecasts that go out to our customers. We, as I say, we use almost all of the sensors on all of these, on both stereo spacecraft as well as on the SDO spacecraft. The AIA images are fantastic. You've seen some really wonderful movies. They've opened up the eyes of the forecaster to new capabilities, new ways to look at the sun, new ways to try and predict those flares and those CMEs, which is one of the hardest things that they have to do. There's very little that sets the flare in motion that you can observe, and SDO and AIA in particular provide new look, and adding the stereo spacecraft provides a global look that are beginning to allow the forecaster to create new and more accurate forecasts. In addition, we use the stereo view to look at the CMEs coming off of the sun and identify where they're going, whether or not they're going to hit Earth, and whether or not they will provide space weather here at Earth. So these data provide key information for protecting our nation's critical infrastructure, allow power grid operators, satellite controllers, emergency responders, the aviation community, all to respond to these space weather events. As I said, solar flares are one of the biggest forecasting challenges. They disrupt the HF radio communication for commercial airlines, and that happens instantaneously. It's not something we have much lead time. So as soon as you see the flare going off, that's impacting the commercial airline's ability to communicate with their aircraft. We also see a loss of GPS signal on some of these flares, and also impacting radar systems. The coronal mass ejections create some of the largest space weather storms here at Earth. There are estimates that the very largest events could knock out our power grid and cost trillions of dollars. They can also destroy satellites with potential impacts of billions of dollars. And again, as I mentioned, they cause airlines to lose communication, especially on polar flights, where they actually have to redirect those flights around the polar region when there are space weather events. So these new discoveries that we've just heard about help us understand the mechanisms, how and why solar flares and CMEs erupt from the sun, which will in turn improve our ability to predict these eruptive events. And with the improved predictions, we at the Space Weather Prediction Center will provide our customers with more accurate forecasts of space weather storms so that they can take mitigating actions and protect their systems. Thank you.
Okay, thank you very much. We'll open the floor to questions in just a second. I just wanted to mention first that there are materials available online from this press conference. There are speaker PowerPoints, movies, and some scripts of their remarks available at www.nasa.gov/SDO. Also, a word to anyone who might be tuning in on the web. If you want to ask questions on the chat, you need to log in. So first we'll take questions from the floor. Do we have anybody who wants to ask a question here?
Hi, I'm Irene Klotz with Discovery Channel. Are the diameter of the sun's distance always tied to the solar flares and the coronal mass ejections, or is that not a set aspect that you look for, that you discovered?
I think we are about to learn what that means, that in some cases flares go off and apparently go off by themselves, not much influenced by what happens at long distances. But we've seen many cases now, particularly over the last few weeks, where much of the solar surface seems to be involved in these eruptions. So it's a mix of things. Sometimes things happen fairly locally, sometimes things happen extending over the full 1.5 million kilometers from side to side on the sun. And we have yet to learn what the mix is and exactly why the sun chooses some scales in some cases and others in other cases.
Bert Schwarzschild, Physics Today. Earth loses its magnetic field a few times every million years. We're overdue for that now, I guess. How bad would things get for our technological society if our geomagnetic field went for a short time to zero?
We can only speculate, of course, and I think we can hypothesize that there would be a dramatic increase in a lot of the energetic particles that are deflected by our magnetic field. And so there would be potential for some serious damages to our technological systems. Other space weather events might not be impacted. One of the concerns is what happens to the ionosphere during all of that. There are a lot of connectivities between the different altitudes of space. And so I personally don't know exactly how it would impact it. I'm only speculating, but I anticipate that certainly there would be a larger influx of energetic particles that would then... And it's bound to happen sooner or later. It's happened repetitively over the millennia, and sooner or later it will happen again. In fact, I believe that the North Pole is moving quite rapidly. The South Atlantic anomaly is also changing position. So there are indications that the internal core of the Earth is a very dynamic and changing environment. But I'm not sure that anybody's actually predicted when this next event will occur.
I think I'll just add to it and just to point out that there is also a more beautiful side to these geomagnetic storms. We see aurora. Every time aurora happens, it's a geomagnetic storm happening. And I think people in the equatorial region will be able to see auroras.
Hello, Harvey Lyford, freelance. I would just like to get an idea of the time frame of these discoveries. You showed images from August. Was that the first time you had established these relationships, or has this been going on longer, or just how new is this?
Well, from the very first observations with SDO, we saw even small events seem to impact large regions of the sun. And because we're scientists and not very clever, we had to be sort of beaten over the head, which is what the August events did. And we went searching for some kind of causality. And so I guess it's been in the last couple of months that we've been working this picture together. And once you've seen something, then lots of things that you've seen in the past all seem to fall into place. I sort of look at it sort of like seafloor spreading, that before Ewing dragged his magnetometer over a seafloor ridge, people for a century had noticed that Africa fed into South America, that plants and animals were very, very similar in the two very separated locations. But no one could imagine the physical processes that would cause such an event. And so it was dismissed, and people who talked about it subsequently were ridiculed. But once someone measured the magnetic field patterns on both sides of the ridge and realized the seafloor spread, that all of a sudden everybody understood a lot of events that had been puzzling. I think that's where we are right now.
Me? Okay, I'm Dave Perlman from the San Francisco Chronicle. I am assuming that flares and CMEs, like sunspots, there's a periodicity of, 11 years or something like that. Is there any kind of periodicity that's over a larger scale? That is to say, would you expect this year's sunspot minimum or maximum, whatever it is, would that kind of periodicity also occur in larger cycles? That is, one period being great, and then is there a 11 times whatever the number might be? Is there a different kind of periodicity there?
Go ahead, Carl.
Okay. There are reports of different lengths of cycles. They go from the 11-year cycle to an 80-year cycle to several hundred-year cycles.
How many year cycles are you saying? It's hard to hear you because that speaker doesn't seem to work well.
There are reports of different lengths of cycles, and they are based on sunspot numbers that have been measured over the past 3.5 centuries. They're based on things that have been found in geological records. They're not understood. It's not clear whether they're real cycles or whether they're patterns that are found simply because there are changes from one cycle to the other. There are some things that we do know, that sometimes the sun shuts down almost as a whole, like during the Maunder minimum in the early 1600s. There were no sunspots for a period of 40, 50 years. There was still some space weather, but much reduced. But even that is not understood. The theory of what generates the magnetic field in the interior of the sun is in a way still in its infancy. It's a really big problem. The sun is a big thing, and it's a big problem to try and do that. So we don't know how to predict the kinds of cycles. We don't know why the sun has an 11-year rather than a 13 or 20-year solar cycle. We see the same thing in other stars, so the sun is certainly not unusual in that respect, and we have a lot to learn about the cyclic behavior.
You mentioned, just to follow up, you mentioned geological consequences. What might those have been?
There are geological in the sense that you can dig around in Earth and find them. You see changes. You can drill ice cores in Arctic or Antarctic ice, and you can see from year to year that there are changes in, say, some of the atoms that are formed by high energy processes high in the atmosphere that find their way into that ice, and you can measure those changes. If you think about the link of solar variability into climate, then you can start using deposits in sandstone, say, where you can see changes from that there are 11-year cycles and there are longer trend cycles on top of that. But separating the internal dynamics of the climate from the driver of the sun is a really difficult thing. Would you like to?
Yeah, I would just like to comment that in fact, even forecasting just the 11-year cycle, how big it will be in exact timing, is a very, very important problem, and one that we work very hard at and don't do very well at. There are a lot of systems, satellites in orbit, other technologies that are impacted on that 11-year cycle, and those people who operate and maintain those systems would really like to know, are we up against a large solar cycle? For instance, satellites in low Earth orbit will require more boosting. This International Space Station and other endeavors like that require more attention during solar maximum. And so for planning purposes and protection purposes, they would really like forecasts of the next 11-year cycle, and that's about as far as we go. And it's a very, very challenging problem.
Thank you.
Rich Monastersky with Nature. I wanted to ask, what is it specifically that allowed you to connect these different events? Was it measurements of the field lines changing, or was it modeling of some sort?
It was a confluence of things that the unique aspect of the Solar Dynamics Observatory is that it observes the sun all the time. And in particular, the atmospheric imaging assembly that we have looking at the sun in extreme ultraviolet is sensitive to all temperatures within the solar corona. So if something changes in temperature, it can't escape our notice. It just shifts from one filter to another. We look at it all the time. There are no breaks in the observations. And we look at it with high cadence. So even if something is really fast, we can still track it. So in a sense, that's what the new view is. And that's what some of the things you were looking at here, that when a flare goes off, its main signature is in the X-ray domain. When one of these big filament eruption happens, its main signature is at much longer wavelengths in the extreme ultraviolet domain, not necessarily visible with the same instrument, except this one does. Now, combining that with the special view that we have with the stereo spacecraft, so that we actually know there's a new active region on one side of the sun that we haven't seen yet from Earth is new. And if we combine that with our modeling, where we say, well, we have a fairly high fidelity representation of the magnetic field, so we can experiment with what the field is doing and compare that to the observations, we have something that enables a discovery like this.
And then one follow-up, is there anything specifically that's improving, from this discovery, that's improving your ability to forecast, or is it just the hope that this kind of discovery will help in the future?
It's a little bit of both. I think that the research that's presented here is more in the future realm in terms of improving our forecasts. Certainly the connectivity and the vantage point of these three observing platforms has provided a very unique view. On the other hand, the data itself, the SDO data, all of the instruments on the satellite have provided our forecasters with more detail and more high cadence, more spectral resolution than they've ever had before. And so even using their techniques that they've developed over the years, using other similar sensors with lower cadence, lower resolution, lower temporal resolution, this just provides a much better platform from which to observe and forecast those active regions and try and identify whether or not they're going to flare.
There are studies right now in the literature already that have argued that changing things high in the atmosphere of the sun play a role in destabilizing the field. And I think that observations like this are now going to give those a very strong boost in trying to make those in real three-dimensional, time-dependent, full-sphere models, rather than the theoretical abstractions that they have until now mostly been focusing on.
Okay, we have time for a couple more.
Rick Lovett, freelance. This is mostly for Dr. Title. Sorry, this is loud. Could you, you talked about sympathetic eruptions, and could you talk a little bit more about the history of what those were and what we knew when, and so that we can put this in historical context a little better? Thanks.
I guess the first ones were mentioned long before I was born. But for as long as I remember, periodically there'd be interests in sympathetic flares. In late 60s and early 70s, there were, can only be described as acrimonious discussions about whether coronal mass ejections were driven by flares or whether coronal mass ejections were things in and of themselves. So these events have been around and argued about intensively in various spurts. I think that in the last sort of 5 years, people have been looking at the topology of the magnetic field. And what I think we're seeing in the August event, and then 2 months later, as Carl showed, the same region of the sun going unstable, is that we have a metastable topology, and it gets kicked, and it releases a lot of energy that's stored high in the atmosphere that triggers these events. And so now we have a kind of smoking gun that we can look for to understand these sympathetic events. And if you want to see these things in better detail, we have the images that SDO produces are 4K by 4K. And so it takes about 6 HD TVs to show an image properly. We have downstairs at the NASA booth a special display that's essentially 4 HD TV screens all on one screen. And so you can see most of one of these events in all the resolution that SDO provides. And it's really pretty spectacular, and it's a lot of fun to play with. I hope that answers your question a little bit.
Jonathan Amos, BBC News. Could you tell us again the distance between these events, and also whenever I speak to solar physicists, I always like to ask them the difference between a coronal mass ejection and a solar flare, and I'm never sure in the last 10, 15 years I've got a very good definition on the difference between the two. So if you could give it a go.
The first one is much easier to answer than the second.
I'm waiting for the second one.
Thank you. The first one, the full diameter of the sun is 1.4 million kilometers. And if you measure that with an extra pi in it around the circumference, it gets to be a little more. But it goes up to a few million kilometers from end to end. The relationship between coronal mass ejections and flares, as Alan just indicated, is one that's been studied for the longest time. And part of the problem is that, as I said, you see these things at different wavelengths, so it's not always clear what causes what or how they're related to what. But essentially, a coronal mass ejection, in its definition, is something that's thrown out from the sun and reaches the interplanetary space, and eventually from there can propagate to any of the objects in the solar system, so all of the planets. A flare is an impulsive release of energy that's seen primarily in the corona itself. The relationship is one that's still puzzling us. We have seen cases with SDO where we see a very large eruption, an enormous release of energy going into forming a very large opening angle coronal mass ejection into the interplanetary space, and it's a minute flare as measured in the GOES X-ray signal. We've also seen cases where there's a very strong flare and hardly any coronal mass ejection associated with it. But they're basically the same phenomenon in the sense that there's a sudden release of energy, and it can take different shapes. It can go into thermal energy eventually and just glow for a while, or it can go into large-scale motion energy and just throw out material, and it depends on exactly the environmental conditions which of the two gets most of that energy. Is that fair enough? All right.
From an Earth perspective, though, what do we receive in terms of particles or magnetism or whatever between the two?
Yeah, the flare, which is typically an X-ray emission, those X-ray particles travel at the speed of light, arrive at Earth, and will impact the ionosphere. And that's where you start to lose your HF communication. Ham radio operators all know this very, very well. So that's a very immediate and much more impulsive type event. The coronal mass ejection, which may originate at the same place and at the same time, travels more slowly and may take 1 to 4 days to reach Earth. And it's more of a cloud of particles and magnetic structure. But when that hits Earth, it's a very different impact. Those particles, that magnetic structure, impact with the magnetosphere that Lika showed earlier, and that starts to really impact a different part, mostly at high latitudes, but even in the big storms down to mid-latitudes. Again, affecting the ionosphere, but now adding a whole host of energetic particles to the mix, which have their own impacts on satellites and humans in space, and even humans on aircraft. So they're manifestations of the same original event, but they have very different impacts at Earth.
Okay, Lisa, go ahead.
Hi, Lisa Grossman from Wired.com. This is for Rodney. You just mentioned that the forecasters now have more detail than they've ever seen before. And I was wondering if our current methods for forecasting are still sufficient given all this new data, or if they're going to need an update.
It's a challenge. Until now, we have used mostly empirical relationships and historical events, sort of a seat-of-the-pants knowledge of what's happening to develop the forecast, and they're very much probabilistic forecasts. We are now just beginning to introduce the physics-based modeling that's required to provide more accurate forecasts with a longer lead time. It's a bit of a slow process. If we compared ourselves to the Weather Service and the big weather models that are used today to predict the weather here on Earth, we're back where they were 50 years ago, introducing those first weather models, and sometimes those models may not do as well as the really experienced forecaster who could just tell from an active region complexity how it's going to behave. But we know we need to introduce these physics-based models to really develop more accurate forecasts with longer lead times. So it's a bit of a long process, and fortunately we have today's computer power and numerical techniques are quite amazing, and we're quite successful in our initial forays into this.
I think I'm going to add to that, and that is what you're seeing are really a bunch of research satellites that are providing observations for forecasting. So space weather forecasting, or the science of heliophysics, is very much in its infancy, as Rodney mentioned. And we are really using research satellites to do our forecasting right now.
Okay, we have one more question from the chat, and then we're going to have to stop.
This is from Nancy Atkinson, University Today, and she asks if you could elaborate, are there regions on the sun where the magnetic field lines repeatedly originate, sort of like fault lines on Earth?
Where they repeatedly originate?
Where the
Is this the dipole?
Sorry, where the magnetic field lines repeatedly originate.
I don't know how to answer that. The magnetic field on the sun comes from the deep interior, but why it chooses to emerge where it does, we do not now know. We know that there are phenomena that are called active nests, where there are successive generations of active regions coming up in the same location, sometimes up to 6 months apart. You'll see a whole series of them come up one after the other. Again, it's something that is yet to be studied. So yes, there are in a way such preferred regions, but they're fairly weak in their appearance. Most of the time, we don't know where new magnetic field is going to emerge on the surface of the sun.
Okay, thank you very much. We've run out of time. Just want to mention, in terms of the screens that Dr. Teitel was talking about in the exhibit hall, they're at NASA booth number 111 here in Moscone West. We'll have our next press conference will be at 11. It's only 10 minutes away, and that's going to be on new views of urban heat islands.